Okay, let's get started. So we in yesterday's class we couldn't finish what I wanted to finish. So let's take off again from where we stopped in the class. So we'll talk about null spaces and image spaces. So in this context, what we said is, let's say you are going to look at a transformation of the type y bar equal to au bar. Okay, and a we have said is we will write this in terms of a bunch of column vectors, okay, where y is in an n dimensional space and u is in p dimensional space. Okay, we took this example where a was an operator that transforms from a flow rate space to height plus concentration space, right. So, A we said is a matrix that does this linear transformation, okay, and the size of A was 2 by 3, 2 rows and 3 columns, okay. That is because our output space was of dimension 2 and our input space was of dimension 3. So, in this context, A is a linear operator, or A is a matrix representation of linear operator, okay. That is what we talked about. And then I said that if you have formally done a linear algebra course in your undergrad, you might have covered this concept of 4 fundamental subspaces of A. Okay. In this course, we are going to talk about only 2 fundamental subspaces, primarily because the remaining 2 subspaces are the same subspaces of A transpose, and that is what we talked about. The last part, do not worry about that. As far as we are concerned, we are going to talk about null space and image space. Okay. So, that is what we said. Okay. So, let us take that same motivating example, but because it is sometimes a bit difficult to visualize in 3D, we will just take a 2 by 2 example. So, let us look at that blending problem. So, you have okay, and let us say that f out is not an input. Okay. Now, this is a problem for chemical engineers. This is usually one of the first problems that that is done in an undergrad control course. There are flow rates in a tank, and there is a flow rate in the output, and the output flow rate depends on the level, the height in the tank. Okay. So, this is a standard problem that is done in chemical engineering. So, in that particular case, and there was a question also where when we talked about blending system. Okay. So, we will actually say that F1 and F2 are the inputs, okay, and outputs are height h and concentration or the mole fraction of species A. So, we are going to mix two guys F1 and F2, and we are going to mix them so that we get the desired concentration of A. Okay. So, that is the problem. In this particular case, the matrix A becomes a 2 by 2 matrix. Okay. So, the matrix A is transforming from an F1 F2 space to an HX space, actually sorry. Okay. So, that is the example that we will consider. The example that I considered 2 days back was where you had F out. So, F1, F2 and F out was the 3-dimensional space. That is not the example that we will consider now. Okay. And we are going to talk about image space and null space. Okay. So, these are the spaces that we are going to talk about. Okay. So, let us say our A has a form, let us say F1 is dilute and F2 is a concentrated stream. Okay. If F1 increases, height is going to increase, if F2 increases, height is going to increase as well. Okay. So, both of them have a similar effect on the height. So, therefore, what we are likely to get in the first row is 1 1. Okay. And if a dilute stream increases, then the concentration will go down. If the concentrated stream increases, then the concentration will go up, right. So, this guy is going to be, let us say -1 and this guy is going to be 2. Okay. So, our A matrix might look something like this. Okay. So, what we want to find out is what is the image space of this and what is the null space of this. Image space is also known as the column space, null space is also known as kernel. Okay. So, we are talking about y equal to or y bar equal to Ax bar. Okay. When we first introduced matrices and in yesterday's lecture also, I said that we want to talk about matrix A in terms of its column vectors, right. So, this matrix multiplication we said is going to be represented as a linear combination of these column vectors, right. So, this will be x1 multiplied by w1 bar plus x2 multiplied by w2 bar, okay, which in this case is going to be x1 1 minus 1 plus x2 multiplied by 1 2, okay, which is going to be x1 plus x2 and minus x1 plus 2x2. This is y1 y2, okay. So, let us talk about image space. What does image space mean? Image space is the space in the HX space which can be reached by a linear transformation, okay. That means you let x1 and x2 vary arbitrarily and that entire subspace that is formed by that variation will form the image space of A, okay. So, as you can see, any point in this x and h space can be reached by choosing arbitrary values of x1 and x2, okay. So, the image space in this particular example is this entire 2-dimensional space, okay. That is the image space, okay. What is the null space of A? Null space is defined as x1 and x2 such that Ax bar is 0 bar, which basically means simultaneously you want to satisfy x1 plus x2 and minus x1 plus 2x2 equal to 0 0. The only possible way for this to do that is x bar equal to 0 bar. Okay. So, we have a trivial null space. The null space for A bar is just the origin. Okay. Now, let us take another example, the same example, but let us say F1 and F2 were both having the same mole fraction. Let us say F1 had mole fraction of 0.1, F2 also had mole fraction of 0.1. Okay. What does that mean? No matter what you do, you are unable, by mixing those streams, you will not be able to change that mole fraction, right. So, how is that case going to be represented? That case will be represented with A looking something like 1 1 minus 1 2. Okay. That is how your this guy is going to get represented, sorry, not 1 1 minus 1 2, 1 1 0 0. Okay. So, let us talk about what is image space of this. So, y equal to Ax bar equal to 1 1 0 0 multiplied by x1 x2, which is equal to x1 plus x2 and 0, right. So, no matter what you do, okay, no matter what you do, the image space is only going to be the x axis or the h axis over here. Let us say you increase flow rate F1, you are going to increase the height. You decrease flow rate F1, you are going to decrease the height. You increase flow rate F2, you are going to increase the height. Let us say you increase the flow rate F1 by 10% and you decrease the flow rate F2 by 20%, okay, you are going to change the height over here, but you are never going to be able to change x, the concentration, right, because you are mixing two streams with the exact same concentrations. Got it? So, the image space in a case like this is going to be this guy. Rest of it is going to be complement of the image space. Okay. There is no way you can effect any change in the mole fraction XA. It is not possible, it is impossible to do that. Okay. Let us talk about null space. Yes, sorry. Question. Yes, so the question is concentrations will still be limited to maximum concentrations that we are putting in. So yes, I mean, so there are two things to this. Okay, I said that we are talking in terms of deviation. Okay, so we are talking in terms of deviation from the current value. So let us say your concentration is 0.1 and 0 and 1, pure A stream and pure B stream you are mixing. Okay, initially you have 50 liters per minute and 50 liters per minute coming and mixing, right, which means outlet is going to be 50% A, 50% B. Okay, that is your operating point. Okay, so along that operating point you have the leeway of going plus 50%, you have the leeway of minus 50%. Mathematically speaking, okay, there is nothing that, when you make a linear system, there is nothing that prevents it from going beyond that. Okay, the thing that prevents it from going beyond that is that there is a kind of a non-linearity, saturation non-linearity that comes in. Okay, that saturation non-linearity is going to look like this. So anything that is beyond 0.5 will get truncated at 0.5, anything that is below minus 0.5 will get truncated at minus 0.5. This is a hard non-linearity. Okay, a linear model is incapable of capturing that non-linearity. So, how do you, in physical situation, how do you handle this situation? By implementing constraints, by saying that between minus 0.5 to plus 0.5 I am linear, I am not allowed to go beyond 0.5, I am not allowed to go below 0.5. In fact, in reality you wouldn't even give yourself so much leeway. In reality you will say that beyond 0.2 or minus 0.2 your linear assumption itself is not going to work. Okay. So, when you are making a mental model of it, think only in a very small vicinity of where you are operating. Okay, do not think globally, but very good question, extremely good question. And this is a constraint when you are using linear control. At the same time, linear control is used for keeping the systems near the operating point. So, let us say you have a reactor and the reactor temperature is 300 degrees Celsius and your conversion is 80% and therefore you get purity of the system to be around 0.7, right. You are going to go only in a small vicinity of that, okay. So, if your operating condition is 300 degrees Celsius, you are not going to operate it below 250 or below above 350. If you go below 250 or if you go above 350, there will be alarms that will go on and the operators will switch off and take everything in manual mode. So, your controller actually won't be allowed to go over there. That is what happens in reality in a plant, okay. But extremely good question. So, we are only talking about in the vicinity of of our operating conditions, okay. So, what is null space? So, null space is the entire x1 and x2 such that y bar equal to 0 bar, okay. Y bar is x1 plus x2 0, right. So, what is the null space? 1 minus 1, okay, where x1 equal to minus x2, that is the null space, okay, or so span of 1 minus 1 is the null space. What does that mean? That means if you increase flow rate F1 by 1 liter per minute, simultaneously decrease flow rate F2 by 1 liter per minute, your height is not changing because net flow rate in has not changed, your concentration is not changing. Why? Because purity of stream 1 and purity of stream 2 were same, therefore your concentration also is not changing, okay. So, image space is a subspace of your Y space, null space is a subspace of your X space, okay. So, if you change F1 and F2 by the same amount but in opposite direction, there will be absolutely no change in Y. So, 1 minus 1 space is the space which will be reflected onto origin in the Y space, that is what that means. So, if we were going to this is going to be our null space. Okay, so you might think, let us say this is a fictitious example. I will actually make what could be one more example. So, let's consider A was say 1 1 and say 0.1 0.1, okay. I am not sure whether we can get this in this particular example, okay. In this case, what is going to be image of A? image of A is going to be x1 plus x2 and 0.1 x1 plus 0.1 x2, which is equal to x1 plus x2 multiplied by 1 and 0.1, which means if in the X space this line is going to be your image space. Okay. So, it is not possible for you to go anywhere in the direction perpendicular to that line by changing flow rates F1 and F2. What is null space of A? Is y bar equal to 0 bar, which implies x1 plus x2 multiplied by 1 0.1 equal to 0 bar, which implies x1 equal to minus x2. So, this is going to be your null space. Okay. So, any point on this will get reflected onto the origin in y. Okay. So, that is what this particular case means. Okay. One example for this could be, let us say f1 and f out were your manipulated variables and f you kept at a constant value. Okay. So, if you increase f1 by 1, your height will increase by 1, but your concentration will increase by 0.1. If you increase f out by 1, your height, maybe we should say, decrease by 1 and decrease. So, if this could be something like this, in which case your 1 1 will be your null space. Okay, but let us not go over to that fictitious example and confuse ourselves. Okay, but this is the concept of null space and image space. Okay, so let us just recap. We took the example of mixing of two fluids. Okay, we said that let one fluid be pure A, another fluid be pure B, and we change the flow rate F1 and F2. Both height and X can be changed. Okay. Then we took another case where we said both the fluids were of the same purity. So, let us say we are mixing 50% A plus B with 50% A plus B. There is no way you can make this change. And then the third case, actually I actually now thought of one more example in the third. This actually does happen. Let us say you are changing flow rate F1 and F2, okay, and let us say F out was under perfect control, F out was always equal to F1 and F2. So, therefore, we did not have to worry about height. Let us say someone, an engineer, decided that the two controlled variables are purity of XA and the purity XB. Okay. What is going to happen? XA and XB, XA increases by 0.1, XB will decrease by 0.1. Why? XA plus XB equal to 1. So, that could be another example. Okay. So, in that case, your A matrix could be something like, let us say F1 is increased, XA is increased by 0, XA is increased by, let us say 0.1, XB is decreased by minus 0.1. Let us say flow rate B is increased, this will be increased by 0.2, this will be decreased by 0.2. Okay. So, if you look at the image space, So 1 2 becomes the image space, okay, and if you see the null space, x1 equal to x2 becomes the null space, okay. So that's what it is. Cool. Okay, good. Okay, so finally we come to this singular value decomposition. Okay, any matrix L or any matrix A can be represented in this particular form, where U is U1 bar okay. U and V are orthogonal matrices. What orthogonal matrices means? Basically it means U transpose equal to identity, V transpose V, or V transpose also equal to identity, okay. And S has a very interesting form. Okay, depending on whether P is larger or N is larger, okay, only the diagonal elements of S are going to be positive values, all the non-diagonal elements will be 0, okay. And the MATLAB command to do that is going to be SVD. What we will do tomorrow in the MATLAB session, let us take this example, let us look at SVD. We will take these 3 examples, you know, 1 1 minus 1 2, 1 1 0 0, and this one 0.1 minus 0.1, 0.2 minus 0.2, and we will see what we get. Okay, what we are going to get is, for first example, sigma 1 and sigma 2 will be positive numbers, sigmas are always positive or 0. In second and third cases, sigma 1 is going to be equal to 0, sorry, sigma 1 is going to be some value, sigma 2 is 0. In the third case also, sigma 1 will be a value and sigma 2 will be 0, okay. The other thing that you will see is that in second and third example, the last vector on U bar will be representative of the null space, okay, and first vector in V which is V1 bar is going to be representative of the image space, okay. So V1 bar span of U1 bar is image of A, and span of V2 bar is null space. We will take this example in the MATLAB session tomorrow.